Hi everyone, today in Integrated Math 2 we're going to go over Chapter 7, Lesson 1. Here are the objectives. Make sure you write them down in your notes. Alright, so let's go over perpendicular bisectors. The perpendicular bisector theorem is saying if a point is on the perpendicular bisector of a segment, then it is equidistant, which means equal, from the endpoints of the segment. So, for example, we know that CD is a perpendicular bisector. Remember, it makes this symbol, which also you would also know that you have 90 degrees in there, which is why this is marked, of AB. Then we know that this side, AC, is equal to side BC. And the converse is just saying the reverse of that. So it goes backwards for this one. The Circumcenter Theorem. The perpendicular bisectors of a triangle intersect at a point called the circumcenter, that is equidistant from the vertices of the triangle. So, equidistant, once again, is equal from the vertices of the triangle. So, notice that this is where they all meet. That's why it's called the circumcenter of the triangle ABC. So, because of that, we know that PB is equal to PA, which is also equal to PC. And that's what that theorem is saying. Then we have angle bisectors. The angle bisector theorem is if a point is on the bisector of the angle, then it is equidistant from the sides of the angles. So, for example, we have if ray BF, which is this one right here, bisects this angle DBE, then we know that FD is perpendicular with the ray BD, which is why we have this little marking here to say it's perpendicular. And then we know that FE, right here, is a perpendicular bisector of BE, which is why we have this one here as well. And if we know that, then we can say that DF is equal to FE. So these are the same. And then the converse, once again, it's just saying the same thing, but it's going backwards. So we're starting with this, and then we're going to that it's bisected. So the InCenter Theorem. The InCenter Theorem is when the angle bisectors of a triangle intersect at the point called the InCenter, that is equidistant from the sides of the triangle. So P is the InCenter of this triangle. And if that is true, we know that PD, PE, and PF are all equal to each other. Alright, so now let's go over example 1. We want to find each measure if Q is the InCenter of this triangle LJK. So we're trying to find the measure of angle QJK. So QJK. So we want to find this one here. But we don't have any other information right next to it to find it. But because we know that it's an InCenter, we know that this is a whole triangle that can help us. So we're going to say that A, to find this, well, one thing that we do know is that we do have a triangle. And we do have to measure the angles of some of the triangles, just not this particular spot that we need. So we can say that the measure of angle KLP plus the measure of angle MKN plus the measure of angle NJP is all equal to 180 degrees. Because we do know we have a triangle. Then we know that KLP. So KLP, well, we know this degree right here is 26. And I also know that this one's 26 because I know we have an in-center. So I'm going to say 2 times 26, because I'm just doubling it, plus the measure of MKN. MKN. I know these are both 29 once again. So I'm going to say 2 times 29 plus, well, I don't know what that is, the measure of angle NJP is equal to 180. When I multiply and then add these, I'm going to get that it's 110 degrees plus a measure of angle NJP, which is equal to 180 degrees. Well, if you subtract 110 over to both sides, you get the measure of angle NJP is equal to 70 degrees. But if we look here, NJP, that's this whole angle here. I don't want that whole angle. I only want half of it. So remember, we can also, but we do know it's half of it. So if you're trying to find the measure of angle QJK, we know that is equal to half of 70, which is equal to 35 degrees. So the measure of QJK is 35 degrees. All right, so now let's try and find B. QP. So QP right here, we have no idea what this is. But I do see that there's a 90 degree here, which I know with the reflexive property, there's another 90 degree. That means that I have a 90 degree triangle with part of the segment that I'm trying to find. And so this is a triangle. Oops, I'll mark the whole thing best as I can. So there's a triangle more or less here. I know 2 of the sides, but I'm trying to find the third side. And then you have a right triangle. So you should be thinking right away that we have the Pythagorean theorem, which is a squared plus b squared is equal to c squared. A squared, let's just say it's PQ, or QP, squared, plus b squared, the next smallest side, so 20 squared. And c squared is always going to be the biggest side, so 25 squared. So then we're going to get QP squared plus 400 is equal to 625. I'm going to subtract the 400 to both sides, and you get that QP squared is equal to 225. Get rid of that squared, square root both sides. Then we find out that QP is equal to 15. And that's it. There we go. Nope, not 15 degrees, just 15.